Welcome to EEL 512, Electronic Circuit Analysis. Chapter 2, Electronic Circuit Analysis, Silicon Controller Rectifier, SCR, Application. Part 1. In this chapter, we're going to learn how to understand the structure and operating principle of an SCR and evaluate SCR applications in power electronic circuits. Part 1. Understand the structure and operating principle of an SCR. In this topic, we are going to identify the internal PNPN semiconductor layer, describe the function anode, cathode, and gate terminals, basic structure and operation of SCR. In a PNPN semiconductor structure, commonly found in devices such as thyristors and GTOS, the internal layers consist of a P-type semiconductor layer sandwiched between two N-type layers, followed by another P-type layer. This forms a four-layer structure with alternating P and N regions. An SCR is a four-layer PNPN device. It has three terminal, anode, cathode, and gate. Turn on, signal applied to the gate current. Turn off, anode current interruption or force commutated. Next is latching current versus holding current in SCR. On this slide, we're looking at the difference between latching current and holding current in an SCR. In power electronics, these are two important parameters that control how an SCR turns on and off. Latching current, denoted as I sub I, is the minimum current required to keep the SCR on right after it's triggered. This ensures the device turns on fully. It's important during the turn-on phase, and its value is usually higher than the holding current. Holding current, denoted as I sub H, is the minimum current needed to maintain conduction once the SCR is already on. It's important during steady operation, and its value is lower than the latching current. In short, latching current is about starting conduction, while holding current is about maintaining conduction. Next is the mode of operation of SCR. There are three modes of operation. The first is the off state, where the anode is assigned a positive voltage, the gate is assigned a 0 voltage, disconnected, and the cathode is assigned a negative voltage. The SCR is not conducting current, even if a forward voltage is applied between the anode and cathode. Only a very small leakage current flows. The SCR acts like an open switch. Second is the on state, where a positive signal is applied to the gate and a large current flows from anode to cathode. The SCR acts like a closed switch and remains on even if the gate signal is removed, as long as the current stays above the holding current. Lastly is the reverse blocking. In summary, there are three main modes. First, reverse blocking. The anode is at a lower potential than the cathode, meaning the voltage is negative. No gate signal is applied, so the SCR stays off, blocking current. Second, forward blocking. The anode is more positive than the cathode, but without a gate signal. The SCR still remains off and blocks current. Third, forward conduction. The anode is more positive than the cathode, and a gate signal is applied. This switches the SCR on, allowing current to flow. In short, both reverse and forward blocking modes keep the SCR off, while forward conduction turns it on. So for the SCR application, SCR, or Silicon Controlled Rectifier, applications are primarily in power control and switching, especially where high power and voltage are involved. They are used to control the flow of electrical current, acting as a solid-state switch. SCRs are found in various devices, from home appliances to industrial equipment, and even in electric vehicles. Example SCR. In phase control, SCRs are used to adjust the power delivered to electrical loads, like in dimmable lights and motor speed control systems. Meanwhile, in rectification, they are used in rectifiers to convert C to DC power, especially in high-power applications like high-voltage direct current, HVDC, power transmission. Motor control. SCRs are crucial in motor control systems, allowing for precise control of motor speed and torque. Thank you, and see you in the next video.